I'm Yang Hua from the University of Hong Kong. Today I will present Best Scheduler. It's a generic communication scheduler for distributed deep neural network training acceleration. And this is a joint work with ByteDance. The last talk talks about pipe dream and is a great work for model parallelism. And in this talk, let's see how to optimize data parallelism. So as we know, data training, the DNN training is very compute hungry and time consuming. For example, it takes 10 hours to train a ResNet 50 model using one TPU. To speed up the training, we can use more devices. And currently, there are two approaches, data parallelism and model parallelism. Data parallelism is a preferred approach in existing machine learning frameworks. And using data parallelism with 1,000 TPU, we can achieve state-of-the-art training time for ResNet 50 and BOAT. And in this work, we focus on data parallelism. In data parallel DNN training, the whole dataset will be trained for many epochs. And in each epoch, the dataset will be partitioned into mini batches. And in each iteration, the worker does forward propagation to generate arrays and then does backward propagation to calculate gradients. Then the gradients are synchronized among workers using some communication architectures like all-reduce or primary server. And in this figure, we can see the computation and communication operations. Here, for example, F0 here is the forward computation of layer 0. The computation and communication operations form a dependency graph. And in this figure, we can see, take layer 0 as example. The push 0 operation depends on backward 0. The pull depends on push 0, and F0 depends on pull 0. Machine learning frameworks build and execute such a dependency graph according to the dependencies. By default, the communication operations are executed in a FIFO way from the last layer to the first layer. In this figure, the green rectangles are push tensors, and the yellow rectangles are pull tensors. So they are executed in a FIFO way from layer 2 to layer 1 and then layer 0. Previous work, like P3 and TIC-TAC, identified the problem with FIFO, that is, FIFO doesn't overlap communication with computation well. And the solution is communication scheduling. That is, we can partition large tensors and change tensor transmission order. In this contrived example, if we partition the tensors and assign higher priority to the tensors with smaller indexes, then we can achieve a 40% training speedup. Previous communication scheduling solutions, like P3 and TIC-TAC, are deeply coupled with specific framework implementations. Like P3 is implemented for MXNet parameter server, and TIC-TAC is for TensorFlow parameter server. Also, this work focuses on empirical results. However, in real world, we have so many different training setups, including different machine learning frameworks like MXNet, TensorFlow, and PyTorch. And for each machine learning framework, we can use either parameter server or all-reduce for gradient synchronization. And the network transport can be TCP or RDMA. So we believe that communication scheduling is valuable to general DNN training, not just one specific setup. And this could benefit the whole community and industry to utilize the expensive GPU cycles more efficiently. And to fulfill this vision, the key question is how to do communication scheduling in a generic way that can work in all different setups with minimal modifications to existing frameworks and achieving scheduling optimality. We observe that no matter which machine learning framework, communication architecture, or network protocol we use, the underlying dependency graph structure is intrinsic for DNN training. And based on this observation, we propose a generic tensor scheduling framework, Best Scheduler. I will show 2 points in this talk. First, we design a unified scheduler framework that abstracts tensor scheduling from various different setups. And second, we propose one principal scheduling algorithm that's guided by theory and works well in real world. So what are challenges here? The first challenge is to be generic to different machine learning frameworks. As we know, there are two types of machine learning frameworks, imperative framework and declarative framework. How they build and execute a dependency graph is different. And second, some frameworks like TensorFlow and PyTorch have a global barrier between two consecutive iterations. And this wait for all barrier, as shown in the figure, would make any scheduling ineffective. The second challenge is to adapt to different runtime environments. In real world, the overhead of scheduling and tensor partitioning is not the same for different system setups. So how to balance the performance gain with scheduling overhead is a very important issue. So now let's see how to address the challenges. To make batch scheduler generic, the key question is, well, should we implement batch scheduler in the framework communication stack? So in this figure, we can see that in the communication stack, the top layer is the user code that declares a neural network using framework front-end API. The middle layer is graph execution. The engines builds and execute a dependency graph. And the underlying layer is message-level communication libraries, including gRPC, MPI, or NVIDIA Nico, and they are based on TCP or RDMA. So to be generic, we cannot modify the framework engines or communication libraries. So we decide to design batch scheduler to be a unified layer between framework front-end API and framework engines. For each machine learning framework, we have a plugin that wraps each original communication operation as a unified task abstraction, contask, and then that scheduler call will partition and schedule the tasks using some algorithm. So in this way, the same piece of scheduling code can work across different machine learning frameworks. The unified abstraction, contask, is a wrapped communication operation, like push one tensor, pull one tensor, or all reduce one tensor. It abstracts framework-specific implementation details and exposes 4 interfaces. The first interface is partition. The batch scheduler call calls this interface to partition a large contask into multiple subcontasks with tensors no larger than a threshold. And the threshold partition size is a very important system parameter, and I will talk about it later. The remaining 3 interfaces, notify ready, start, and notify finish, are designed for scheduling. So to schedule contasks, batch scheduler call needs to interact with framework engines to get the scheduling control. So we may ask, is there a generic way to do this? And our answer is dependency proxy. The dependency proxy is just a norm operator created by batch scheduler. And in this figure, for simplicity, we only show the backward propagation operation and a communication operation of one DNN layer. And for each DNN layer, we add a proxy. The dependency proxy does 3 things. First, when the backward operation is finished, the proxy operation can be started by framework engine to notify the core that the gradients have been calculated. Second, when core decides to start the task, it will call the start interface to let the proxy finish. And then the communication operation can be started. Third, to know the completion of communication operation, we add another type of proxy right after the communication, and this proxy only generates completion signal using notify finish. Also note that the proxy implementation differs for imperative engines and declarative engines. So as mentioned before, some frameworks like PyTorch and TensorFlow have a global barrier between 2 consecutive iterations, and this barrier would make any scheduling ineffective. So how should we handle this case? Here, we also use the dependency proxy to cross the global barrier. And the basic idea is out-of-engine communication. Specifically, we replace the original communication operation with an asynchronous operation. And the asynchronous operation starts the actual communication in the background and lets the global barrier pass. So in this way, the actual communication are run by core outside the engine. Also, to build correct dependencies for each layer, we add another type of proxy to block forward computation until its corresponding communication is finished. Take OLReduce as an example. This figure shows a modified dependency graph. The red lines here are the original dependencies, and the green lines are the layer-wise out-of-engine dependencies. Here we can see that the global barrier still exists, but it doesn't affect communication anymore. So after figuring out the unified abstraction to interact with different frameworks, the next problem is about scheduling. And first, we will show that priority queuing is the optimal scheduling for minimizing the time of one iteration in an ideal case. That is, assume the partition size is infinitely small and the preemption can happen immediately without any overhead. Then, for either parameter server or OLReduce architecture, assigning higher priorities to the layers that are closer to the input layer is an optimal solution. However, in practice, partitioning and preemption have certain system overhead. And next, let's see how to address. To realize preemption, previous work like Tic-Tac and P3, they adopt stop and wait approach. That is, they send a tensor, wait for its reply, and then send the next. This approach cannot fully utilize network bandwidth. So our approach is credit-based preemption. It works like a setting window, and the credit size is the window size. So instead of sending one tensor, we allow multiple tensors in a setting window to be sent concurrently. And here, the credit size is a very important system parameter. Typically, a larger credit size leads to better bandwidth utilization, but less timely preemption. So how can we find the optimal partition size and credit size? They are affected by many different factors like network bandwidth, number of workers, or DNN models. And we decide to search their best values during runtime. Specifically, we use Bayesian optimization for auto-tuning. Bayesian optimization tries to minimize the tuning overhead to find an optimal solution for the general objective function. And typically, it runs for tens or hundreds of iterations at the beginning of training. Next is evaluation. We implement batch scheduler for MXNet, PyTorch, and TensorFlow. And to use batch scheduler, the user only needs to add 2 lines of code to his program. The test bed includes 60 machines, each with 8-volt GPUs and 100 gigabits per second bandwidth. For comparison, we use vanilla machine learning framework as baseline, and we also present the linear scalability. First, let's see the scalability of batch scheduler when training with different number of GPUs. Here, we show the training speed of 3 models, VGG, Rastat, and Transformer, using different number of GPUs from 8 to 64 in MXNet parameter server RDMA scenario. And the numbers in the parentheses are batch scheduler's speed up. Here, we can see batch scheduler can achieve up to 170% improvement, and its performance is close to linear scaling. Next, let's see how batch scheduler works with different machine learning frameworks. Here, we show the training speed of VGG using MXNet, TensorFlow, and PyTorch. We can see that batch scheduler can achieve up to 2 times improvement compared to the baseline. Here, we also show batch scheduler can adapt to different bandwidths. We change the bandwidth from 1 to 100 gigabits per second, And the fixed scheduler bus here shows the training speed without auto-tuning, and the tuned scheduler bus here shows the training speed with auto-tuning. First, we can see that we can achieve consistent speed up in all bandwidth settings, and also without auto-tuning, the training speed is lower, and sometimes its performance is worse than the baseline. In summary, bus scheduler is a generic tensor scheduling framework for distributed DNN training acceleration. It provides a unified abstraction for tensor scheduling and supports multiple training frameworks with minimal code change. We also propose a principal tensor scheduling algorithm with automatic parameter auto-tuning. And this is a source code of bus scheduler in the GitHub. Thanks for listening, and if you have any questions, I will be happy to answer them.
Just one question. So I saw that some of your authors are industry. Are you attempting to actually use this in industry in ByteDance?
Can you speak your question a bit louder?
Sorry, can you hear me now?
Yeah.
Yeah.
Okay.
So I'm just wondering, since this is like practical, right? Whether there has been any attempt to use this in industry, in ByteDance, for example, where some of the authors are.
Yeah. It's conducted in ByteDance.
Hi.
Yeah.
Sorry. Hi, Mingyu from Shanjiao University. Good work. And my question is that you have introduced the proxy to mark the dependency between the communication and the previous iterations. So my question is, why not directly use BP to directly communicate with, for example, the communication task to ask it to start the communication?
Sorry, the last part of your question, can you speak again?
So you use a dependency proxy to indirectly for a previous iteration to send a message to ask the communicating task to start. But my question is that why not directly use, for example, the BP directly communicates with the communication task and ask it to directly start without proxy?
Yeah, so we use dependency proxy in order to achieve generality. So if without proxy, then we may need to modify framework engines in order to achieve communication scheduling.
But in your figures, the proxy is still in the engine. I mean, you still need to implement the proxy inside the engine, right?
Yeah, but actually, we implement the proxy outside the engine, and we put this proxy to the engine. So we do not modify the source code of engine. Yeah. So in this way, bus scheduler can be generic across different machine learning frameworks. Otherwise, we need to modify the source code of every machine learning frameworks, right?
Okay. Thank you.
All right. Let's thank the speaker.